In this video, I'm going to show you how I use these convolutional neural networks to play the classic kids game Connect 4. The algorithm that I use to train these is the infamous AlphaZero algorithm. This is Google DeepMind's AI algorithm that beat the best humans in the world at games like chess and Go. And I really want to explain exactly how these neural networks work, not just treating them as a black box. Like what math calculation is actually going on here. I actually think Connect 4 is the perfect example to understand exactly how a convolutional neural network works. Mathematically, it's like an image that is only 6 by 7 pixels big, and you can see exactly how the AI finds patterns in the board that it needs to play Connect 4 well. I've built this interactive explorer where we can go into the brain of the neural network and see exactly how it's picking up on these patterns. This interactive notebook runs in your browser, and there's a link in the description where you can try it yourself and play Connect 4 against this AI. So you can play around with it and dig inside yourself and see how it works. So how exactly does AlphaZero use neural networks? Well, mathematically, what's going on here is we have a function that I call f sub theta, and it depends on some parameters theta, and this function will give us advice about which moves are good moves and which moves are bad moves. So to be more precise, what I mean here is that our function is going to input positions that look like this. These are represented as arrays of integers inside the program, and it's going to represent a board position where there are some pieces on the board. And what this function is going to do is it's going to give us advice about, of the 7 possible moves, they start at 0 here because we're using Python, which of those moves are good moves and which of them are bad moves. And higher numbers mean good moves, lower numbers mean bad moves. So you can see in this situation, the AI is saying move number 1, playing in the column right here, is probably a good move. Move number 4 maybe also is possibly a good move, playing right here. But the other ones, playing in 0, 2, 3, or 5 or 6, these are all bad moves. So don't play here or here or here or here or here or here or here, because those were bad moves. And these are all going to be positive numbers. We're going to use that later on. And they all sum to 1. That makes sure that the AI can't just say every single move is good, right? It has to decide how it's going to allocate its budget towards which moves it actually wants to recommend. So this function f theta is exactly what that convolutional neural network is doing. And I'm going to show you exactly what the parameters mean, what do the thetas mean, and how do they enter into converting this kind of board position, which is an array with 0s, 1s, and 2s. How does it get converted into this kind of vector of numbers? But first, I want to talk about something even more fundamental, which is how are we going to find this expert advice function in the first place? So the really surprising thing about AlphaZero is it doesn't have any data. So the 0 in AlphaZero means learning entirely through self-play, learning just by playing itself, starting with 0 knowledge. So how exactly are we going to figure out which moves are good and which moves are bad? And this is very different than normal neural networks. So in a normal neural network setting, you do something called supervised learning, and you have a data set that you use. The classic example is the MNIST digit recognition task, where you're given pictures of handwritten digits that look something like this, and you have to figure out what digit is being represented. So again, this is a function that inputs an image and outputs probabilities of what digit does it think it is. Does it think it's a 4? Does it think it's a 7? In this case, it actually thinks it's a 9. In this kind of situation, the way we train our neural network is we are given human data. So for example, someone might say, hey, I meant to draw a 4 here. This is supposed to be a 4. And we would take that information and we would say, hey, the AI algorithm right now thinks that this is unlikely to be a 4. It is wrong about this image. And therefore, we should change the parameters a little bit to boost up this probability. So this probability is going to get boosted up a little bit. And then the next time we get an image, we'll be more likely to correctly identify a 4 based on this human data that we had. Now, this approach is really great, and it has unlocked a lot of power in machine learning. Even ChatGPT sort of starts with this kind of algorithm, but this will not work at all for the way we want to train our algorithm. So can we just copy human games of Connect 4? Well, no, we want to get something that is superhuman at playing these games. Well, maybe we could generate some data by playing some other algorithm, and we could just copy, this other algorithm that we're doing. And the thing is, like, if you're just going to do that, why don't you just use that algorithm? So the AlphaZero algorithm is really doing something different here that is very different than supervised learning. It is really learning through experience, through trial and error. And this is something called reinforcement learning. The core idea in reinforcement learning is that you are both generating experiences and learning from them. And this has received a lot of excitement in recent years, where it's hoped that this kind of reinforcement learning algorithm will let AIs escape the bonds of human data and move on to, tackling problems in the world like robotics and things like that, where they can learn from themselves. Some people have famously said that human data is like the fossil fuel of AI, right? It's very good to get a head start, but ultimately we're going to have to move past it and move into algorithms that can learn from themselves through experience. And that's what we're going to learn about in the AlphaZero algorithm. So how exactly does it do it? The thing we're going to do is something called a bootstrapped training loop. And bootstrapped is coming from this expression of picking yourself up by your bootstraps, something you can't actually do in real life, but does work for machine learning. And it's really a 2-step process. So first, we're going to take our expert advice function, and we're just going to use it to create many example games. And then in step 2, we're going to take the games that were generated in step 1, and we're going to use that to improve the function f. And then we're just going to repeat. We're going to go step 1, step 2, step 1, step 2, over and over and over again. And every single time we do it, our function f will get a little bit better. And you might think this is exactly like the bootstrapping. You're pulling yourself up from nothing. If the function f theta doesn't know anything, how on earth is this going to work? And we're going to see that the key to making this work in AlphaZero is that the games that are generated in step 1 are done in a very clever way so that they are a higher quality of play than just the expert f theta itself. In other words, we're going to layer something on top of f theta in step 1 to make really high quality games that are smarter than the expert currently is. That way, when we go to step 2, the expert actually has something it can learn from the games that were generated in step 1. In fact, the games we generate also are going to come with a very particular signal, which is going to tell us about which moves in particular the expert was wrong about. So there's going to be some moves where the expert missed a really good move. There's going to be some moves where the expert thought a move was really good and it turned out to be really bad. And we're going to have this special signal that's going to tell us exactly which moves those were, and we're going to use that to learn something. And that brings us to the next problem, which is how exactly are we going to do this? How are we going to generate games from this expert f theta that are smarter than f theta itself? And the secret is this thing called Monte Carlo Tree Search. In fact, I made a whole previous video about Monte Carlo Tree Search and exactly how it works. Monte Carlo Tree Search can work just on its own without an expert at all. It can generate a pretty good AI algorithm just by running simulations of what it thinks will happen in the future and using those to guide how it will choose the next move. To make AlphaZero work, we're going to take our expert f theta and put it inside the Monte Carlo Tree Search to make it even smarter. And the secret is to do it in a very particular way. So the heart of the Monte Carlo Tree Search algorithm is scoring how good moves are based on simulations, but including not just how they've done in the past, which is what I call the average. That's the average of how good a certain action was in all the simulations we've done so far, but also adding on an optimism bonus. And this optimism bonus is making sure we test moves out in a smart way. If there's a move that we haven't tried very much, we'll have a lot of optimism about that move, and therefore we will go and try something new. It's this combination of exploiting the best moves with the average and exploring them with optimism that makes the Monte Carlo Tree Search algorithm work so well. This is traditionally done with something called the UCB algorithm, where the optimism bonus just depends on the number of times we have tried each thing. Things that we haven't tried, we have a lot of optimism about, and things that we've tried a lot, we have less optimism about because we already know how good or bad they are. I actually made a whole video about this too. If you really want all the details, you can go check that out. In our particular case, for AlphaZero, what we are going to do is take our expert f theta and put it inside the algorithm. And the secret is leave the average alone and put the expert only in the optimism bonus. So the expert f theta only gets included in the optimism bonus. And this is sort of like telling us, the expert says, hey, this move I think is pretty good. You should give this one a little extra optimism. You should check that one out a few more times than you normally would. And the really smart thing about doing it this way is that eventually the average will overrule the expert. So because the expert is only being used in this optimism bonus and is not being used at all in the average of all the actual simulations we've ran, eventually, if the expert is wrong about something, the simulations, the real simulations we did, will overrule the expert, and this average term eventually will beat out an expert that is wrong. A really good example of this is what happens right at the beginning when the expert knows nothing. When we start our neural network, it's going to be totally random. It's going to say all the moves look equally good to me. I don't know anything. And when we do that, we just get the pure Monte Carlo Tree Search algorithm. So in the situation where the expert doesn't know anything, the optimism bonus is equal for all the moves, and that's what the Monte Carlo Tree Search algorithm does. If you want to know more about this, I really highly recommend you go watch that previous video that I made on Monte Carlo Tree Search. I really think it's a really cool algorithm that works even without any neural networks or anything like that. Okay, and to be even more mathematically precise, the formula that we're going to use is what is called the PUCT score, the Polynomial Upper Confidence Tree Score. This is replacing the UCB algorithm that we used in Monte Carlo Tree Search, and it's adding in this expert advice. And here will be the only big formula in the whole video. Here's the formula for the PUCT score. And it says that when we're trying to choose where in the tree to move down, what we do is we score things based on a combination of the average plus this function, which is encoding the optimism bonus. And the optimism bonus is directly proportional to what the expert function f theta is saying. So remember, the expert function had to output positive numbers, which means we always have a positive amount of optimism. And it had to have a budget where it's summed to 1. So it sort of spreads out the optimism amongst the moves that it sees, and it can have more optimism about the moves that it thinks are good, and moves that it thinks are bad, it will have less optimism about and try them less often. All of this is multiplied by this term over here, and this term ensures, again, that moves that we haven't tried very much will eventually go and be revisited. So this is giving more optimism to things that we haven't tried very much, and it's scaled by the expert. This is the perfect combination of using the expert and exploring things in the natural way that seems to work really well in AlphaZero. And to see what this looks like, we can finally go into the interactive notebook. Okay, so here I am in the interactive notebook. If you want to be able to see the code, you can press this button to toggle app view, and then it'll show you all the code. But if you just want to play along, you can put it into app mode and just play along without knowing anything about the code. And The game that you can play against the AI appears here. You can play Connect 4 by pressing on these buttons on the top row up here. And the AI is playing the blue pieces, and it will play back. And if you look over here, there's a nice big bar chart that is showing you what the AI is thinking about this particular move. Every single move is represented by an action number, playing in column 0, column 1, column 2, column 3, and so on. And there are 2 bars for every possible action. The 2 bars show you the actual simulations that it ran. That is the solid filled in bar, which I have labeled as MCTS for actual Monte Carlo Tree Search. And the shaded bars over here are the neural network output. So this is what the neural network thinks about the position. And you can see that they are not exactly the same. So the neural network has a certain amount of recommendation about each move, and then we're validating the actual play through simulations and deciding what move is the best based on the results of our simulation, incorporating that average term, which move to actually play. And in this particular case, it did a lot of rollouts of playing in the middle. And I believe this actually is the best move in this situation. Let's see how it thinks if I try something else. Let me try going like this and see what it does. So there, it blocked me in the middle. And again, both the neural network and the actual things are quite confident that blocking me is the way to go. Let's see, what else can I do against this AI? Let me try building a tower like this. Again, it's very certain about what to do over here. Maybe I will try going over here. Okay, now look at this. Now I have it 3 in a row this way. Oh, and it's trying to build up a 3 in a row this way. This is a perfect situation to show you something interesting, was that this move that it just played of playing in the corner was not highly recommended by the AI. So in other words, this move playing in the corner, the AI thought it didn't have an idea that this was a very highly recommended move. It actually recommended playing in column 5. So it recommended playing right down here. But then the algorithm ran a bunch of simulations a la Monte Carlo Tree Search. And what it did is it figured out that based on the results of the simulations, playing in column 0 is actually quite good. So the Monte Carlo Tree Search overruled the AI expert through its simulations, and that is why the AI played in column 0 in this particular case. This is exactly the training signal that is used to train the algorithm. When there are situations where the Monte Carlo Tree Search with the AI expert finds a move that is different than what the AI expert recommended, then it will update the probabilities. So what happens is we take all the games, we take all the positions like this, and we move the probabilities to make them more like the Monte Carlo Tree Search. So we try to change the parameters to move this probability up more. We say, when you're in a situation like this, you should play in the corner. That is the move that we found was the best. You should do that kind of move. When you are recommending playing in column action 5, that's the wrong move. You should lower this probability. So the neural network output is adjusted to try to match the Monte Carlo Tree Search. And in particular, we're using something called the cross entropy loss to measure how different these two things are. And then we're doing gradient descent to try to make them more similar. And I believe 3 Blue 1 Brown is in the process of making a video series about what is cross entropy loss. So I won't try to explain it here. Go watch his video. It'll be much better than anything I could ever do. The cross entropy loss is just measuring how different these things are. And our training is just trying to make them more similar by minimizing the cross entropy loss. And here is a plot showing the results of all this training. The cross entropy loss that I was talking about is shown here on the y-axis in green. And you can see that at the very beginning it is very high. And what this means is that when our neural network is initialized, it doesn't know anything. And the moves that it's seeing from Monte Carlo Tree Search are totally alien to it. The distance between what our neural network thinks and what is actually being validated by simulations in the actual game are very, very different. That's because our expert is very dumb. It doesn't know anything. So we have a really high cross-entropy loss to begin with. But then what we do is we play a bunch of games and we use those games. Every time the neural network is underestimating what it should do, we boosted the probability up. Every time it's overestimating what we should do, we shrink the probability down. And then through this training process with gradient descent, we are lowering the cross-entropy loss. And that means that what the neural network thinks is getting closer to what is actually happening in the games. And this is taking a dramatic downswing over here in generations 1 and 2. So I call running these 2 steps, I call that a generation. So a generation is running a batch of games with the current version of the algorithm and then using gradient descent on those games to improve the expert. And you can see that generation 2 has a really big, huge amount of improvement in generation 2, and then it keeps going down and down and down, going pretty monotonically for a while. In blue here, I have plotted the win rate against the baseline. So the baseline I started with is what we had at generation 0. We were winning 50% of the games to begin with. It is a very simple Monte Carlo Tree Search with 200 rollouts. This is actually a very bad algorithm. 200 rollouts is not really enough for the algorithm to play Connect 4 at a human level. This is very easy to beat. And so our algorithm is quickly able to beat it. By generation 5, it is winning like 95% of the games. As we keep training, we keep doing step 1, step 2, step 1, step 2, going through the generations, making new versions of the AI. Eventually, what starts to happen is we start to have this bumpy little texture where the cross-entropy loss goes down and we're sort of overly memorizing that batch of games, and then it goes back up again when we get a new batch of games. But the general trend line is still that it is going down over time, and I ran it, I think, for 44 generations before I stopped it. So after 44 generations, we get down to a cross-entropy loss of about 1. It turns out 1 is pretty close to the minimum we could possibly get due to the sort of background entropy that's just in this problem. Again, you should definitely check out 3 Blue on Brown, who I'm sure will do a great job of explaining what this entropy thing means. And so overall, at the end of all this training, our algorithm gets up to something like a 98% win rate against this very stupid Monte Carlo Tree Search AI that we're comparing against. And not only that, the convolutional neural network that I was using throughout has learned some really interesting patterns. And that's what I want to show you next. How is the convolutional neural network actually calculating these things? And how is it learning the patterns that are being used to play these games really well? Okay, so if we come back into the interactive notebook, I can show you this convolutional neural network explorer that is letting us see into the convolutional network and see exactly what it's thinking. If you check this box, it will show you what's going on in the game that you're playing against it. The position I want to analyze is actually from this game where the AI was playing itself. So this is the position where the blue opponent has just played over here and has created this threat of having 4 in a row. And it is now red's turn. And of course, every good human would know you have to block this turn. And indeed, if we look at see what the AI is thinking from this position, you will see that the AI is saying, look, there's a 0.94 out of 1. You got to play in this column. And this diagram over here is showing you the entire 3x4 next layer of the neural network of what is going on. And you can see that this box over here corresponds to this neuron over here. And this neuron is very highly activated. This neuron is very highly activated. That means that the AI is detecting there is something interesting going on in this little 4x4 box. And that is leading to having to play, a recommendation to play in this column very strongly. But what exactly does this mean? Like, this is very confusing. How exactly is it calculating this? And the problem is that most of the time when people explain what convolutional neural networks are, they stick to 2 dimensions, where a convolutional neural network is actually happening in 3 dimensions. So I've made this little animation for you in 3 dimensions to show you how exactly is it calculating that something interesting is going on in this box. So in this animation, I've shown the exact position that we were just looking at. So red and blue pieces, and the red pieces need to block the 4 in the row threat that the blue pieces have just made. And the first thing to understand is how is this grid of red and blue and blank squares represented in the computer? Well, it's represented as an array of integers, but we take that array and we turn it into a 3D picture by making different what are called feature planes. So this is what that looks like. So we go into the 3rd dimension, we make these feature planes. The first feature plane that I'm showing you here is the feature plane of which squares are empty. And you can see that we've gone from 3 colors, empty, red, and blue, to just 2 colors, black and white. And black represents a 1. That means this is an empty square. You should treat this as an empty square. And white means, hey, there's a piece here. This is not an empty square. So that's the first feature plane. So we take that feature plane, we put it somewhere, and we make another feature plane. The next feature plane that is being made is the red pieces. So every time there's a red piece, we mark that with a 1. The next feature plane, you could probably guess, is going to be the blue pieces. So all of the blue pieces are marked with a 1. So these are the 3 feature planes that contain the information about where the red pieces are, where the blue pieces are, and where the empty squares are. And we could stop there. We could just have the algorithm work on these 3 feature planes. So it's sort of a 3D grid, which is 6 by 7 by 3. In classical image processing, you also have 3 planes. You have the red plane, the blue plane, and the green plane. So RGB values for images, and every pixel has an RGB value. So you stack up these 3 planes kind of like that. We could do that, but I actually included in my neural network, I included 2 more feature planes that I thought would be useful for the AI to learn. So the first one was which squares are occupied. So of course, we already told the AI which squares are empty. It could figure out on its own which ones are occupied, but I just gave it that information to give it like a little boost. Maybe this will be useful to you, right? Knowing which ones are occupied. So we include that in our feature plane. Now we have 4 feature planes, but I also included one other one that I think is very important, which is this feature plane tells the AI which moves are possible moves. So I have marked all the squares in Connect 4. If you played in that column, where would you play? And so for example, if you played down here, you would appear in the bottom, but if you play in this column, you would appear on the top. So these ones represent what would happen if you play in that column. And so I have a feature plane of all the different actions. So altogether, in the AI algorithm that I'm actually running, we've taken our input board position and we have turned it into 5 feature planes. Each feature plane is an array of 1s and 0s of size 6 by 7. And so altogether, we have a 6 by 7 by 5 feature plane kind of 3D block of numbers that will then go into the rest of the convolutional neural network. In the actual AlphaZero algorithm, there were something like hundreds of these feature planes. And that's because in the game of chess, they used one feature plane per type of piece. So the knights would get their own feature plane, the pawns would get their own feature plane, and so on and so on. And they also included the position from, the previous move and the move before that. So by the end of all of this, they had literally hundreds of planes in their algorithm that was fed into the convolutional neural network. For us, it's just 5. So now let's see what happens with these 5 feature planes. How are they actually turned into a number? What is the actual math operation that is being done here? So we take these feature planes, and what we're going to do is we're going to select a 4x4 region. This is called a filter of size 4x4. I've started with the top left because this is the sort of 0, 0 coordinate, and it was up to me to choose this size of 4x4, but I know that 4x4 is something special in the game Connect 4. So that's why I chose 4x4 as the size, and we have selected the top left region. Selecting the top left region on the board corresponds to selecting a cube of numbers of size 4x4x5 in our feature planes. So we have this box of numbers 4x4x5 coming from our feature planes and our choice of this 4x4 region. This is a 4x4x5 array of ones and zeros, and this is where we're going to finally use the parameters of our neural network. So our neural network is going to have 4 times 4 times 5, which I believe is 80 numbers, and those 80 numbers are 80 different boxes that I have overlaid on top of our feature planes. And these are the actual numbers that are going to multiply against the numbers from the feature plane to get a final answer. So we take all these numbers, there's 80 numbers in total, and we're going to multiply each number by the feature that it sees at its location. So because the features are all ones and zeros for us, what this is actually going to do is this is going to delete a bunch of these numbers. So a lot of these numbers will get deleted, and we'll be left with only the numbers where there is a 1. And this lets the AI recognize things like, is there a red piece here? Is there a blue piece here? And it's going to put a sort of a weight on that number. And now what it's going to do is just take the multiplication of those two things. It's going to take the value of the weight times 1. Well, that's just the value of the weight. And it's going to combine all the numbers in this box together to get one final number by simple addition. So we're going to take all these numbers, we're going to add them all together and get one final answer. And that final answer is how strongly the neuron is activating based on the 4x4 feature planes that it saw. So this is taking 80 different numbers and combining them down into one final number based on the features that it actually saw in that square. And then we're going to repeat this process for every possible location that we can put that 4x4 square. So we're going to move it over, do the same thing again, and we're going to take the same 80 numbers and get a new number that is telling us about what is going on in this new 4x4 square. And we're going to move this 4x4 square around all over all the possible places we can go. And because we started with a 6x7 grid of numbers and we're doing this 4x4 filter everywhere, we're going to end up with, at the end of all of this, a 4x3 grid. You see the dimensions got reduced. This is called a, quote, valid convolution, where we're only doing convolutions in the places where our entire 4x4 filter can fit. And by using these 80 numbers and sliding them around and multiplying them by the features we see and adding them all together, we're going to get one final number for each 4x4 region. Okay, so at the end of this process, taking our 4 times 4 times 5 equals 80 parameters and sliding them around on the feature planes and multiplying them by the ones in the feature planes and adding them all together, we end up with this little grid of 4x3, which represents the activations of the neural network. How strongly is it recognizing patterns in the parts of the grid where it looked? And now that we've understood the sort of 3D picture, the architecture of how this thing works, we can look at the actual weights and see what is it actually thinking. So we can see the 4x3 region that I was mentioning before that has been calculated by this first layer of the neural network, starting with the 7x7 board, going to the features, and then converting that by this multiplication by the weights into a 4x3 region. And you can see that actually almost all of the things it has calculated are negative numbers. Negative means not very much is going on. We're going to see exactly why negative and positive is very important in a minute, but I want to focus on this one neuron. This one neuron is the only positive neuron. And this is kind of saying that in this region that corresponds with the location of this neuron, something interesting is happening. We have calculated by doing linear combinations of ones and zeros from the features based on the features we saw here that there is something interesting going on in this location. And if we scroll down a little bit, we can see exactly what is going on in this little representation that shows us the weights that we were talking about. The 4 times 4 times 5 equals 80 numbers that were the parameters of the network. Those are shown in color here on this scale, from -1 being very red to green being +1. And that's shown as the background color of each of these things. And we have the 5 feature planes. And remember, the 5 feature planes were the locations where there's nothing, empty squares, the locations where there are pieces, the locations where the enemy has a piece, and also I added in the occupied pieces and the actions. And those are overlaid with ones and zeros over top of the size of the weights that you see. And you can see something very interesting is that there is some strong pattern happening in the diagonal here. It's all red. And what that means is this is a very negative contribution to the final outcome. If we had a piece here, if we had one of our pieces was in this diagonal, then we would have a 1 somewhere in this diagonal, and it would be a 1 times a very negative number, and that would contribute a very negative amount to this neuron activation. Unfortunately for us, we have all zeros here. So this is 0 times negative, 0 times negative, 0 times negative, 0 times negative. The overall contribution of our pieces to this filter is 0. On the other hand, the enemy pieces have very positive numbers. So because it's a green background color, we see there's a very positive number for weights in this feature plane. And so every time the enemy has a piece on these very positive numbers, they are getting added up and counting towards activating this neuron. So in this case, we have 3 positive numbers, 1 times a big positive number, 1 times another big positive number, and 1 times another big positive number. And this is activating the neuron and saying, hey, look, there's something going on here. The enemy has 3 pieces in a row. So what is the overall effect of all this calculation? Well, the overall effect is to recognize we must not have many pieces on this diagonal. If we did, there would have a big negative number here, and we don't have that. So we're seeing we don't have pieces over here, and the enemy has a lot of pieces over here. So this is a situation where we're saying, oh no, the enemy has a threat that we might need to block. And that is what this neuron is representing. This neuron is specifically detecting this kind of threat, that the enemy has a threat along this particular diagonal. Okay, well, how does this neuron activating over here, how does that translate into the final action? Well, we do it again. So the thing I showed you was the first layer of the neural network, and it is outputting this 4x3 region. And now we have a 4x3 region. We also treat that as features, and we keep going forward with more layers of the convolutional neural network. In fact, I've shown you the entire architecture that I've used here. It's a pretty complicated process. I've shown you the first layer of going from the board to the features to this 4x3 region, but then we keep going and we keep doing more layers of the neural network until we eventually end up with the 7 actions that we want. The 7 numbers that sum to 1 that are all positive that tell us how good things are going. But I've added in this little thing here that tells you the effect of the selected neuron. And what this does is it calculates what would happen in the rest of the neural network if this neuron was turned off. So right now it's at 2.8. If I set it back down to 0, how would it change things? And we're seeing that what it's doing overall is it's adding on a bonus to column 2. So this is contributing to saying that we should definitely play in column 2 in this position. This neuron is recognizing the threat, and then there's something later on in the neural network that is saying, okay, when there's a threat there and we're in this situation, we should definitely play in that column. Now, the observant among you might have noticed in this thing that I said that there's just one 3x4 thing. And that's because I only showed you so far one filter, but actually there are 64 filters, and you can choose which filter you want to look at by using the slider. So when we go from the original Connect 4 position and we use 80 parameters to go down to a 3x4 board, we actually do that 64 times, and we end up with 64 different 3x4 arrays of neuron activations. And I've shown you them here, so you can slide and select which ones are interesting. The negative ones mean nothing much is going on, but the positive ones means the AI is detecting something here. So here's the one we were looking at before. Oh, here's another one that is also detecting the same kind of diagonal shape, different than the one before. Maybe the neural network is detecting it more than once. Here's one. I have no idea what it's doing. This is detecting something like, oh, you can't play up here, but you can play here. So I don't really know what it's doing in this one. So some of them are a little bit more transparent, but some of them are kind of like doing some magic stuff of mixing together numbers that will maybe get used in a later layer in a way that I don't understand as a human. And last but not least, so far I have said that the way the parameters are used is they multiply the features and then they are just added together. These are both linear operations, so doing a linear combination of the input features and adding them all together. But there is one non-linear operation in this network, and that lets the neural network do the if statements. And so you can see here I have drawn what is going on here before the pre-ReLU, before this non-linear activation function called the ReLU. And it is a combination of negatives and positives, like I told you. So we're doing this combination of everything we see, and we get, at the end of it, we get a negative or a positive number. But then we take the answer and we pass it through this ReLU. And this ReLU function, all it does is it says, if it was negative, just set it to 0. So everything that was negative, turn that off, and only let things that are positive pass through. So what the ReLU does is it takes our vector of size 64, and it converts it into a vector of size 64 with only zeros and positive numbers by turning off everything that was negative. So anytime the neuron didn't see something, it goes through this sort of like if statement that says, okay, if you didn't see something, just set it to 0. And if you did see something, then let it through, and maybe we will use that to make our final answer. And by adding in these ReLUs, we give the neural network the power to learn if statements and say things like, if there's a piece here, then do this, if there's a piece here, then do that. And it's sort of this like magical way of encoding if statements with algebra and also this special nonlinearity called the ReLU. So the ReLU just lets positive numbers through and it sets negative numbers to 0. And that's all I think I have to say about this stuff. Please try this out. You can also go down here and put in a manual position by sliding this little matrix around, put in 1s for player 1, 2s for player 2, and then you can see what the AI is thinking in any custom position that you want by sliding around the location with this and sliding around the filters that you're looking at over here with this. Last but not least, I will say that the true AlphaZero algorithm has 2 upgrades that go over top of the algorithm that I just presented. So the algorithm that I just presented is how is it using this expert F theta in the policy, choosing which moves to try, and improving based on the Monte Carlo Tree Search with that policy. But there are 2 improvements to the rollouts being used. So remember, the Monte Carlo Tree Search is doing these rollout simulations to validate which moves are actually good and bad. And so far, they are being done purely at random, trying random moves until we get to the end of the game. And there are 2 ways you can improve that. You can use the expert that we have to do smarter rollouts. So instead of doing them at random, pick moves that are more realistic, that are better moves, and that will give you a higher quality of rollout and therefore more accurate results in your simulations. And you can also make them shorter. The way you can make them shorter is only run them not until the end of the game, but only for a fixed number of moves. Maybe you play 10 moves and then you stop. And then you have to train this new neural network called the value neural network that will then recognize from that position, is this a good position or a bad position? So these 2 things are critical upgrades that really take the AlphaZero algorithm from learning on its own and being pretty good to being like really world-class and amazing. And if you play against the AI in the notebook, you'll discover that it's not actually very good yet. So I'm planning on making one more video on the AlphaZero algorithm playing Connect 4, where I will put in these 2 upgrades and I will have little switches to toggle them on and off, and we can see how much of a difference do they actually make. Which parts of the algorithm are responsible for the really high performance and which ones are sort of optional and just extras. So subscribe if you want to see that when it comes out, but otherwise I hope you will play in the interactive notebook and you will enjoy playing some Connect 4 against AlphaZero.